cool. All right, everybody. Bit of a stretch run here. So we've been talking a lot about programming models. And today I'm going to talk a little bit about something that you might have heard about in a distributed systems class, actually. So who has taken distributed systems here at CMU? A lot of people, because it's a popular class. Who wrote Hadoop code in said distributed systems class? Who wrote Spark code in said you wrote? So really?
I wrote it in my ML distributed systems.
Your ML distributed systems class. Good. Okay. I'm just curious. So a lot of people have seen some of the first couple slides, but not so much about Spark or any of the new stuff. Okay. Good. So let's start with this. So this is a slide that I've shown in this class before. It's two programs. They do the exact same thing. So imagine that I gave you this little library that kind of like allowed you to multiply and add numbers. And let's say you wanted to compute some complex some expression, and you can make various calls to add and multiply, and you can get the job done. And it would be pretty easy for me to throw a parallel for loop, a pragma parallel for around each of those for loops in my library, and I could provide you a parallel implementation pretty easily, right? Not hard at all. And then I rewrote the program this way, and I said, screw this library, I'll do it myself. So which program performs better? So I want to talk to a lot of people today, because this is a, yeah.
The second one is it keeps the cache hot.
Keeps the cache hot. What do you mean by that?
So it's only ever accessing each entry in A and B once.
Okay.
What?
Yeah, I agree.
And so you don't have to, you can exploit some locality because you're looping through sequentially through the arrays, but also you don't overwrite the run. You don't have to remove things from the cache on the second run to do the multiplication and addition.
So let's talk through that a little bit. So that was good. That was good. So you said that it only touches A and B once. I actually think both of these programs actually only touch A and B once, because I only read A once, and I only write. What do I write? I write the end result is E. I only write E once. So both programs. So you're completely right. I know exactly what you're thinking, but I want to clarify it just a little bit, right? So both the input A and the final output E are touched once in both of these programs, but there's really the difference is in the intermediates. And what are you thinking?
We have program to avoid making function times 2, and each of those has memory access.
So first of all, I don't have to allocate the temporary arrays, but more importantly, you mentioned cache locality. Is that what's more important than the footprint? So we certainly don't have to allocate these temporary structures.
You have temporal?
I have temporal locality, or values are produced and immediately consumed. And where is that? Where is that in the code here? Like, how did you conclude that was true? And I agree. Yeah.
So AI plus BI, that value is probably in some register somewhere and it's used immediately.
Yeah, in fact, it's probably not even cache locality here, right? Like in this simple example, this straight line piece of code is going to multiply, going to load A, load B, store the result in a register, load C, multiply C by the register, and so on and so on. So the cache may actually not even come into a play at all in this example. But point taken, absolutely. Like if we had more intermediates here than might fit in the register files, we would spill out to the L1, and we would immediately reuse that. So yes?
There's also the overhead of function calls.
There's the overhead of function calls, but presumably n is pretty large here, so I wouldn't worry about that too much in this particular case. Yeah.
More data around in the first program than in program 2.
Yeah. So think about what's going to happen here in program 1. We're going to load A. We're going to perform one math operation. We're going to write immediately to temp. It's going to go all out to memory. We're going to load temp all the way back in. We're going to do one more math op. We're going to store the temp2 all the way out, and so on and so on. So what I've done here is I've rewritten the program. It may be clearer to read actually in this form. It may not be. You could argue either way. But it is certainly going to be more efficient because I've improved the arithmetic intensity of the program. Or in other words, I've exploited, I've restructured the program so it takes advantage of that temporal locality, right? And so the overall arithmetic intensity of the first version was 1 math op for every 3 reads. Now we've increased that at least to roughly, about 3 math ops for every 5 reads. So the performance on this program, how much faster do you think it'll be? Yeah. Yeah, roughly, the ratio of 3/5 to 1/3. Yeah. And why is that, though? What's the big assumption in us making that?
That it speeds up linearly with the arithmetic.
And what's the big assumption there? That's true.
It's entirely parallelizable.
So what if I gave you, what if I just did, let's say I did 100 math ops in every one of those individual loop bodies. So instead of just adding the 2 numbers, I added another for loop and added it 100 times or something like that. So my claim is that arithmetic intensity is good, but once you're high enough, increasing arithmetic intensity more probably won't be any more helpful. So I agree that we're going to see speed up here that's basically directly proportional to how much we increase the arithmetic intensity. But there's an assumption that I'm making here, and it's not quite that the program is parallel. It's something else. What is the assumption that makes that to be true? Sorry? It's bandwidth bound. So if this program runs only at the throughput that memory can provide, if I decrease the requirements on how much data I need to move over the memory bus, I should see a proportional speed up. If this program is bound by the throughput at which we can execute instructions, further decreasing the amount of memory that we move, or data that we move around, will not make the processor run any faster because it's already running at the rate that it can sustain. So you can, yes?
But you're not decreasing the amount of data, you're increasing the number of operations.
I haven't changed the number of operations at all. These 2 programs have exactly the same number of mathematical operations in them.
But in that statement, you're doing 3 instead of 1.
Yeah, but I only made 1 call to fused here, and I made 3 calls to fused here. It's the exact same math. The exact same number of operations. If this happened to be a computer with an infinite bandwidth memory system, this optimization would have been useless. But the reason why I made this optimization is that I know that a program that has this little math is going to be bandwidth bound on any system that I probably will run it on these days. And therefore, I wanted to reduce the amount of work that the memory system has to do because the whole program is waiting on the memory system to do its job. Make sense? So I didn't change what the program does here at all from an arithmetic perspective. 2 classes ago, I gave you this program. And this is a little bit more code to digest, but if you remember, this was the blur of an image, where we did it in 2 passes. First, we blurred the image horizontally to produce a temporary image. And then we blurred the image vertically, of the temporary image vertically, to produce a 3x3 blur of the entire image. This was the code that we kind of started that lecture with. I ended up at the end of the lecture with this code. And why did I go in that direction? This was from the Halide lecture when I was talking about, well, how would we do things for real if we wanted to do image processing fast? So what's the difference between this piece of code here and this piece of code? Again, just like the last example, they compute the exact same answer. The only difference is sort of the order in which they do the computation and what temporary buffers that they allocate and use. Is there any reason why the second solution is better than the first? Yes?
This has to do with the cache size. So
Okay.
we expect the reduced temp buffer size to be able to fit in the cache size so that we don't have that much misses if we go with the first approach?
So in the first approach, we perform an operation and store the result in a buffer that presumably is large. It's the size of the entire image. And let's say we're taking a photo with our iPhone. So it's an 8 megapixel image. Maybe there's 4 bytes per pixel, so it's a 32 megabyte image or something like that. It won't fit in cache. So that means that whenever this part of the program accesses temp buffer, this is a load from memory. How did this program change that behavior? What did it do to prevent the temp buffer access right here from being a load from memory? Yeah? So we made a small temporary buffer. We said, look, we're going to do the first part of the program and fill up this buffer that size that's big enough or small enough that it will fit in some cache, some level of the memory hierarchy. And then before we generate more of that temporary output, we're going to drain the buffer, essentially. We're going to use the buffer here in part 2. And we set chunk size so that width times chunk size is some amount of data that we know fits in cache. And so the only data that's read from memory is the input image once and the output image once when it's stored. All of the intermediates are always consumed shortly after they are produced, and therefore we're not going to incur too much memory traffic from that. Good. So does this example relate to the previous example? Why did I put these back to back?
It's the same concept, but one operates at the register cache level and one operates at the cache.
Sure. Both of these examples were transforming an input program so that the intermediates were always immediately consumed. They were not, and since they were immediately consumed, they were in cache from when they were produced, right when they were consumed. In this case, I immediately consumed them, like immediately. In this case, I didn't immediately consume them. I created a buffer, and the buffer was sized to fit in cache. So this is going to be, L1 cache locality. The previous example would have been register locality. And if you remember the details of the lecture, had we immediately consumed things, we actually would have computed too much. We would have done overcompute. So I was trading off how much temporal locality I wanted for how much work I really wanted to do. Okay, so these were 2 good examples of globally restructuring our code, reordering the operations, not changing the operations at all, but just reordering them to improve the arithmetic intensity and improve performance. So this is something I want you to think about for the rest of this lecture. Okay, so these examples that we've done throughout class are going to be front and center throughout this lecture. And I want to do the whole lecture in terms of an application like, for example, analyzing the clickstream on the 418 website. Which, if you look at my little web blogs, it's kind of surprising. Why are people looking at the 2013 version of the course? I don't know. But a non-trivial fraction of the web blogs from last night were on the 2013 version of the course. So we should go figure out what's going on. So imagine that the 418 website, so Apache, every time you view the page, we get a log entry. And companies are really interested in analyzing the click streams of their users, right? Like if you're Amazon, you might be like, well, I wonder how they a user navigates the site. I want to know if a user looks at this product and then looks at that product. Those are interesting things I'd like to know. So sometimes we have to make a leap of faith in this class. We need to make a leap of faith. So let's assume that 418 gets really popular and this log gets really big. The log is not that big, trust me. You could probably handle it with grep. But if this was a big website, maybe that log would get very big. Like, for example, Taylor Swift tweets about, hey, I'm going to show up and give a show for this class or something like that, which that is not a guarantee. That will not happen. And then maybe somebody else tweets, hey, that's a good idea. I'm coming too. So we get all these followers start clicking on the website. Maybe Beyonce comes in and says, whatever, kids, and whatever. So this log could just get really, really big, right? So this log of page views can get quite large. And from your distributed systems class, or maybe your big data ML class, you might have studied file systems like HDFS, which provide a mechanism to store really big files over the disks spread across a cluster. Right, so the details of how that's done are not relevant to today, but imagine like I gave you 4 nodes on late days, and we ran an HDFS instance on late days, and I could take this huge file, this clickstream file, and I might chop it up into little blocks and store it, not little blocks, but large blocks, and store it on the various disks across the cluster, right? So I have one big file, 418log.txt. It's divided up into blocks in the file system, and the file system splats that across the cluster, because it's so big that I don't have a big enough disk in my cluster to store it on one node. Makes sense, right? Okay. So imagine that, let's say, Taylor Swift's agent is like, you know what? We know that there's a lot of useful data in this log. We would like to understand a little bit more about our fans, because we'd like to figure out, should we invest in developing an iOS app, or should we develop an Android app, or whatnot, right? So one question might be, what type of mobile phone are all my clients' fans using? Which means I need to go look at this log and do some analysis of it to answer that question. And if I wanted to do that, one way is I could use a programming model like MapReduce. And so I don't assume that you guys have seen MapReduce, but let's just talk about it a little bit. So imagine that I had a class that reads the file, an iterator over every line of the file. Imagine that I have some ability to write an output, and I'll give you one function call. And your only function call in this domain-specific language is called run MapReduce job. And you give run MapReduce job 2 functions. You give it something called a mapper, and you give it another lambda, another function called a reducer. And the input will be this iterator over all lines of the file. And the output will be, well, I'll define what output is in a second, okay? So the mapper is going to get called once per line of the file. Let's just say that's the rules of our domain-specific language. Is if you give me a file, it's a text file, MapReduce job will read it line by line, and for every line, it will call your implementation of mapper. And your implementation of mapper takes as input a line. It parses the string. It grabs the user agent out of the line. What's a user agent? What do I mean by that?
It's like browser using or like EOS and stuff.
Yeah, it's a software the client's coming from. So here it might be hard to see, but where's the user agent? It's somewhere in here. Unfortunately, I don't have enough resolution. Yeah, you can see like Mozilla 5.0. You can see Mozilla on a Mac. You can see Apple WebKit, which would be Safari, and so on and so on. So the user agent, the browser being used to view the site is in that string somewhere. So imagine I write a little routine that parses it out. So that's my parse requester user agent. And then I have another routine which, given a set of strings, returns true or false whether or not it's mobile, right? So I just a little lookup table. And so if it's a mobile client, the mapper is going to emit a key value pair, which says, here's the mobile client, here's the string identifying the browser, comma, value 1. This is your hello world example in MapReduce if you've seen this elsewhere. And then what the system is going to do is it's going to take all of these key value pairs, after all the calls to mapper, and it's going to sort them. It's going to sort them by key, and for every unique key, it's going to call your function reducer. So mapper and reducer are the functions that your application gave my domain-specific framework that were passed into MapReduce job. MapReduce job called the mapper on every line of the file. The execution of mapper created all these key value pairs. The system sorted the key value pairs for you and provided them to your reducer function, where the reducer function is called on every unique key. It gets a list of values, which are all ones in this case, given my application, and it just simply adds up, basically computes the size of the values array. And so this program is computing the number of page views by each type of mobile phone that visited the site. Make sense? This is, for those of you who've seen it, this is more or less the abstractions presented to you by MapReduce or Hadoop. So it should be familiar to many of you. So let's actually design an implementation of this DSL, of this framework now. So here's so let's say we have this cluster, and we had our disks in every node in the cluster. And now I'm going to give you a CPU, because you need to run something. So imagine there's a single core in every computer. And all of them talk to the same file system, so they can load a piece of the file. And here's your code for reference. So the question is, step one is we need to run the mapper function on all lines of the file. So it's like I have this parallel for loop, right? For all lines in the file, run the mapper function. You're implementing this framework now. What is your scheduling policy? There's a lot of answers to this question. So I would like to run calls to mapper independently on every line of the file. How might you do that? Given that the only thing you can load the file from the file system. You can call fopen and move directly to any place in the file if you want. And if you load a place in the file, it will be served by the node where that chunk of the file is. Yeah, why don't you get started?
So I can see that we have only a single CPU per node.
Sure, yeah.
And
Because I just don't want multi-core parallelism to matter in this example. So I just want you to think in terms of nodes.
everything we do is basically reading from the disk.
Yeah?
So that means it's quite I/O bound.
It's quite I/O bound,
And
yeah.
I would to hide this I/O latency, I would assume that we need to launch multiple threads per node.
Okay, yeah, that's actually absolutely true. But for the sake of this today, I just want you to use all the nodes first of all. So we could use the nodes better, and I'm actually going to come back to that at the end of the talk. But for now, the thought experiment is you have 4 nodes. All of them can run jobs. How are we going to parallel map over all these jobs? Well, I would like some specifics of how you will assign it. Yeah.
So the thing is, you probably want to take a chunk of the file, such that the file will probably fit nicely in RAM and other like trash stuff.
Okay.
RAM memory and trash. So then after that, you will synchronize all 4 nodes. Like you request for one chunk, like quite a lot of lines. Once that line succeed, then you probably increase some atomic count to request for the next chunk.
Sure. Okay. So how will you assign work, jobs, and a job is running one call of mapper on a node to the nodes? Sure.
You could just split the log file into like even chunks and just give each node.
I already have.
Right.
The file system has.
So
Yeah.
They could just read through their lines and have their own counters essentially.
Okay. So you're going to just say so specifically you're saying every core will run mapper on lines of the file that are local to that node. Perfectly reasonable. What if they happen to not be equally distributed? If the
You could have like a work queue where they could pull new lines off.
Exactly. So there are a bunch of options here. One is we could just say, you know what, we're going to divide the billions of lines of the file into some chunks equally, and we're going to throw them all in a work queue, and every node is going to say, if I'm done, I'm going to grab the next thing off the work queue, and I will do that work. And I will get the data from whatever disk is necessary to get the data. Or we could do things like what both of you are suggesting. We could say, you know what, maybe perfect workload balance is not the interesting thing here. What's more interesting is to actually leverage the locality in the file system. So let's assign jobs to nodes based on where their source data is. And that has the nice property of not only do you not move data around the machine, you probably can just load a whole block off of disk at once and then do that processing, which would be probably way more efficient than loading a part of the block. Question, yeah.
I guess the idea 2 would just be so much faster than idea 1, because like idea 1 we've got like terabytes of data that we have to communicate.
Exactly. Idea 2 really is a better idea, given that really we're not doing a lot of processing here. Yeah.
I like finding the
Yeah, your idea was good. I was saying, in fact, it had a lot of the first elements, and then you said, and if you wanted to be more advanced, you could do both. So that's why I pointed at you and said, you guys had good ideas. Yeah. Got to make sure that you give credit when credit is due. Okay, good. Okay, so I like these ideas, and you could implement that. In fact, maybe they even have you implement this in your distributed systems class these days. I don't know if you implement MapReduce, but it would be a great assignment to do so. So the mapper, we've got a good strategy for now. Okay, so now we need to keep going, right? So now at this point, where did you store the results of all those maps, right? We have all these tuples. So I'd like to know where are you going to store all these tuples that you generated by running the mapper, and then I'd like to know how are you going to schedule the reduce jobs, where the reduce jobs require your implementation to gather all of the tuples with the same key into a data structure, and hand them off in a call to one of the reducers. So how are we going to do that? Let me move around a little bit. Yes?
Use a hierarchical structure to do the reduce. So you do the partial reduce of each node, and then pass the result of the reduce around, and get reduced again and again and again until there's only one data structure.
Okay, so the solution, just to summarize for everybody, was, look, first of all, we need to do a reduction. We need to figure out for every unique key, what are the list of values associated with it. And that needs to be a reduction across the entire cluster. But your suggestion was saying, you know what, we can make it easier by let's first do the reduction on every node. And then we can do a reduction across only 4 sets of keys, and that's more efficient. Good. Now the question that I have, I like that implementation. The question that I have is, well, what node is going to end up with the final result for which key? So we have a bunch of keys, and each of the keys have a list of values, and that one of the nodes is going to process that key. So how are you going to choose what node gets what key? And keep in mind that this file is way bigger than all the memory we have across our cluster. So how are we going to move that data to the node that needs it? So let's finish off our implementation here. So can somebody prescribe how you're going to do it? So we have a good algorithm now for doing the reduction. Happy with that? Yeah.
Do we have typically there's a master node in these sorts of things?
Well, that's an implementation detail. So you have 4 nodes. You can do whatever you wish. Yeah.
I guess you could just name one, like the master node, and say, everybody report your result back to him.
Okay. But keep in mind that I can't fit the results in memory. Because this is terabyte, this is terabytes and terabytes of data.
Isn't the final result just like a string and a number?
Each tuple is a string and a number. Yes.
So wouldn't each node process the reduction locally if I store that?
Correct. So now we have a string and a list of numbers.
Right.
Uh-huh.
And can it just send that over the network to the master node?
It could. But I still have terabytes of numbers. like, let's assume that the intermediates are huge. I mean, I have all the unique users. Okay, fine. So we could send it all to the master node if you wanted to. Sure. Yeah.
I thought the number of numbers was, I thought we had.
Oh, you're saying because we're filtering down, then, okay, I think we can make that assumption. Sure. Okay, we can send it all to the master node, and now what? What? So you're not going to parallelize the reduction at all, because I still may have like hundreds of thousands of user agents. Well, I have all these unique keys.
Okay, then parallelize that.
Okay.
How about you combining the work queue for like reading it from the file, processing reduction, as well as like a sort of a stream reduction that like one over process.
Well, that's how I interpreted your suggestion, actually, which is at least on one node, as soon as you get new keys, you can start reducing.
I mean, like that would be one on a local node, then there will also be a node that.
But in actual, you guys are actually violating something I forgot, is that you don't know that it's a sum reduction. Given the programming model right now, you don't know it's a sum reduction. So what you know is that when you call reduce, you need to call reduce on every unique key, and that you needed to hand it to a list of all the values associated with that key. So actually, your optimization doesn't quite work yet. It does if you knew it was an associative reduction, you could do that, but in my definition, you can't. Yeah.
I can't imagine how it would work properly if the reduction wasn't associative.
Collect all the keys, make the call to reducer. The reducer can do whatever it wants. So the reduction on any one key, given the semantics of actually MapReduce, are that the reduction is done serially for one key and parallel across different keys. Now, if you're actually running real MapReduce, you actually have a different associative reduction function call if you want to do that, but I've done the simple original MapReduce here. So we just kind of need to pick a processor, or pick a node that's going to process the keys, and we've got to get all those keys over to the processor, right? So if you've taken your fancy distributed systems class, let's talk about how that's actually done in MapReduce. So the way it's done in MapReduce is that the communication infrastructure is this nice distributed file system. If you want to communicate data to another node, you can just write it to a file, and then the other node can pick up that file and do its thing. So imagine that, in contrast to sort of what I just told you, maybe there's 4 unique user agents that we care about. So every node is generating a file, which here are all the tuples with this key, which is kind of doing the reduction that you were saying. It's not doing the reduction, but it's organizing all the data. And then in the reducer phase, we know how many unique keys we have across the cluster. Let's assume that we figure that out. And then we just distribute those keys to the various nodes. And then the node needs to read, let's say if, I think I actually have an example on the next slide. If the node says, OK, I'm responsible for doing the reduction for Safari iOS, let's say node 0 is, node 0 is going to read all of the Safari iOS files across the cluster, bring that together into the list, and then call the reducer function. Now, of course, the assignment, you might want to be smart about this, and the scheduler might say, hey, look, most of the Safari iOS files, this is the biggest chunk, so we'll assign Safari iOS to this node because that will minimize data movement. That would be an optimization, and so on and so on. So this is the implementation, more or less, I'm simplifying dramatically, of Hadoop MapReduce. Yes?
Why don't you put all the Safari iOS values on the same node? Like, why do you split them up like that?
The why I split them up like that is I stored them where they were produced. That's all. So I could put them on the same node, but that's not on one node. But that's not saving me anything. That's equivalent to, I just told you I need to bring them all to the same node to do the processing.
So in that example, you're just assuming like Chrome Glass was all on node 0?
I'm assuming that node 0 parsed a part of the log file.
Yeah.
It found a bunch of lines for node Glass.
And it didn't find, like none of the other nodes found it. Is that what
Oh yeah, I guess so.
Okay.
Yes.
Okay.
Yeah. In fact, that's why I did that on purpose, just to show that. Is imagine that for whatever reason there were no, right? And so if you were a smart scheduler, then you might decide to assign the reduction function to node 0 rather than randomly assign it to another node, because then the other node would have to move the data over the network. Yes?
So you actually don't know how big the reduction, like, data chunk is going to be until you finish that thing.
Not at all. Yeah, correct. Yeah, absolutely. Absolutely. So, and then imagine that like if you're running a MapReduce job, you might run it on a large cluster. So imagine we're running it not on 4 nodes, but like 1,000 nodes. Because everything that we've designed so far would actually scale to thousands of nodes if we had a big log file that could actually make use of that system. So if I have 1,000 nodes, now all of a sudden I have to start worrying about some things that we don't worry about in this class. Like one of those nodes may fail. If I'm running 1,000 nodes over the course of a day, maybe one might fail. It might be a heterogeneous cluster, because there might be some network contention, so they might actually take longer than each other, so I have to do some workload balancing. It could start to get a little bit tricky. So this job scheduler in MapReduce is handling a lot of these responsibilities, right? It's exploiting locality, and just like what I think you guys pointed out, that like remember our implementation 2 was like obviously way better. Rather than move this huge chunk of data to some node to ensure proper workload balance, we're almost certainly better off moving the job that touches that data and scheduling it on the node where all the data is. So at these scales, move the computation to the data is very much the mentality of designing a scheduler. And you might need to worry about node failures. You might need to worry about, like if you're Google, you might need to worry about handling slow machines because you have a cluster with computers bought at different times. Or actually, if a disk is about to fail, it actually might be intermittently failing, so you get lower effective bandwidth. So even though they're actually the same machine, they don't perform the same rate. So you'll have a lot of issues. OK, so now imagine I wanted to write PageRank. So I gave you a very simple example, but using the same 2 primitives, I actually could theoretically write PageRank. My mapper could be mapping over all of the edges, or every node, and I can say for every outgoing link, I'm going to deposit some of my ranking to all of my edges. So I created a tuple which says this is value needing to be put on this edge on the other side. And then the reducer, the system would grab all of the contributions to one vertex, like all of the incoming edges, and the reducer would just sum them up. And that's what I did here. So I can actually implement PageRank, the algorithm that we talked about at length last time, in terms of just these 2 little simple primitives. So I run, I load the graph. Every iteration I call MapReduce job. So let's think about this. is this a good implementation of PageRank? I can give you a couple cool things. This can now scale to an arbitrary number of nodes. It'll handle failures, it'll handle redundancy, it'll handle kind of all the messiness of a cluster. Does this seem like a good way to go about PageRank? And if you don't think it's a good way to go about PageRank, what are some reasons that are concerning you? So yeah, for every node, I'm going to iterate over outgoing links. I will make a token, a key value pair that says add this amount to this node. The system will collect all of those tokens together and say, here are all the updates to this node. I'll sum them all up. I'll update the node, and we'll continue. And I want you to think about your implementation of the MapReduce job. And I also want you to think about the first two examples I started class with. Yeah. It's a barrier between every iteration. Yep. Yeah, we talked in GraphLab last time about signal and some of the asynchronous behavior that they could do to sort of be more efficient. Imagine the comparison to GraphLab if, let's say, that GraphLab div had a barrier. If we use the standard FIFO scheduler in MATLAB, we could actually have the exact same computation. So imagine like drop GraphLab out of your head, drop MapReduce out of your head, and think about how this will run on this cluster of machines. Think about how the data moves.
So you're generating a bunch of values for every node in the mapper.
Yes?
Or the mapper could have just like already started to do the reduction just by storing a single sum instead of all of them.
Correct. And where did I store those values in between?
On disk.
On disk. So I started this lecture to say, this is ridiculous to think about going out to main memory on a lot of the computations we've discussed in class. And PageRank and MapReduce says, you know what? I've got an idea. Using hundreds of machines is really attractive to me. Let me move the entire graph update data structure for this huge graph that required 100 nodes. Let me push it all the way out to disk and back for every iteration. But I've heard a lot about parallelism these days, and parallelism's awesome. That's exactly what a lot of folks were doing not too long ago. And like, wow, MapReduce, this is very, very interesting. We can express all these operations in MapReduce. So let's talk about how the world has changed a little bit in reaction to the fact that if I decided that if I gave you assignment 3, and you said, you know what, I could speed up assignment 3 by using multiple nodes on the cluster. And my mechanism of doing that is storing my graph data structure out to AFS between every iteration of PageRank. That's how I'm going to get 4 times more parallelism by using 4 nodes. You probably are not going to win that race. Right? You're probably not going to win that race. OK. So the main idea of a system called Spark, which in some sense was a reaction to people going, wait a minute here. MapReduce was designed for things where it made sense to go out to disk. Now we're trying to do graph analytics. Now we're trying to do scientific computing in a framework because we're really excited about using all these nodes. That may not be the best idea. So the goal of Spark is to design a programming model for a cluster that gives you the scale-out parallelism, gives you a lot of those properties, nice properties, but can run efficiently out of memory while still retaining the benefits of handling failures, like a node can fail in the middle of your computation and things like that. So the big problem that they had to solve, in some ways there were 2 problems. And when Spark was introduced, the big problem that people were thinking about was like, we want to run in memory, but what happens if we lose a node? If we lose a node, we're screwed. Whereas in the MapReduce example, if we lost a node, its outputs it came from disk, and so you could just load them from disk again and go and start again. So a lot of the motivation for Spark was about fast and highly redundant. I'm going to focus a little bit more on the fast today, because that's actually turned out to be far more meaningful to people. So the key idea in Spark is that we're going to program in terms of a data structure called an RDD. An RDD stands for Resilient Distributed Data Set, which means it's distributed across the cluster. It's resilient, meaning that if any of the nodes fail, we can actually get that part of the data structure back if we ever wanted to. And so the abstraction is that an RDD is just a collection. It's just a sequence, back to your 210 sequence operators. And that there are two things I can do on RDDs. I can transform them to create new RDDs. So RDDs are read-only. So I can map a function on RDD to create a new RDD. And I can execute actions on RDDs, which actually cause me to get data out of them. So if I'm like the driver code or the top level CPU host, if I say, hey, I want to know the length of this thing, I can call count or length, and I can get the RDD's length. If I want the contents of the RDD, I can call a function called collect, which gives me a normal C-style array, which has all of the stuff in it. Okay, so all the code I'm writing today actually is in Scala, because Spark was originally developed in Scala. They have Python front ends that most people use right now. Okay, so this says create an RDD from this huge text file. So I have this big file on disk. I now have a sequence, and the sequence, every element in the sequence is a string, which is a line from the file. Here I'm creating a new sequence, which came from filtering the original sequence using this predicate. So that's my isMobile client. So now I have a new sequence. And now I can filter again, which says, OK, for all the mobile clients, I want to filter again to find only the ones that contain Safari. And then I want to know how many Safari page views did I have, so I'll just call count on the resulting sequence. So you can think about this as a sequence of these operations, where every box I'm drawing here is a sequence, and every arrow is an operation, a transformation, taking one RDD to the next RDD. Make sense? OK. If I wanted to go back to my original example, I kind of wrote it all in one line and didn't assign, I didn't assign variable names to things. So I say I'm going to create an RDD from the file. Then I'm going to filter that, which is going to return an RDD. Then I'm going to map onto that, returning a new RDD. I'm going to do a reduce by key to join all the counts from all the user agents. And then I'm going to call collect, and I'm going to get out an array of string, comma, int, where every string are the mobile user agents, and the integer is the sum reduction of how many page views did I say. So what we just did in MapReduce is expressed in Spark on this slide. Okay. So does this sort of make sense? Following this? Just to check your understanding, here's one where it's not quite a single lineage. We do a number of things, and then I could actually, I say mobile page views is it mobile? And then we can create a tree of operations to say, OK, we might want to know how many Safari page views there are. Or from this RDD, we might want to filter it for Chrome. Split this. I wrote split, which means we'll take the first word in the string, which happens to be the timestamp in my weblog. So this is a list of all the timestamps of Chrome visits to my page. So just notice now that there's a DAG and not a pure lineage. So and Spark often refers to these graphs of computations as a lineage. The lineage is the sequence of RDD operations that are needed to compute some other RDD. So if I want to compute this, that means I have to do that, and then that, and then that, and then that. And so Spark provides you a list of various, in the same way that your sequence library in 210 provided you map and reduce and various operations on data parallel sequences, Spark provides you the exact same thing. And all of the major things you would think of are here. Some of them that are probably not necessarily in your sequence library would be something like reduce by key, which is the operator that MapReduce uses to collect all the inputs up for all of those keys. There's also like a database join, which is an interesting one, which takes two collections of keys and values, and then creates a tuple, which is the value from the first sequence and the value from the second sequence that have the same key. So join is a nice little one to look at. So RDD of key value, another RDD of key and another value, and the type of the output is an RDD tuple of that key value is the tuple of the two values that came before. So that's the type of join. And then, of course, you can, at any point in time, your program can get information out of the RDDs by calling actions. The length of the RDD, the contents of the RDD. So this takes an RDD to a Scala sequence of the same type. You can actually access it from your program. OK, so here's the big question. That's the abstraction. The abstraction is pretty darn clear, right? You have a sequence library. How are you going to implement these RDDs? So imagine that we start from the exact same point that we did our MapReduce implementation from. I have my logs. It's distributed across the cluster. And let's say we're going to go with this simple sequence. So we're going to create an RDD of every line of the file. We are going to take the string and make it lowercase. So that's a map. So we're going from every line in the input RDD is a line in the output RDD. We are going to filter that sequence by mobile page views. And then we are going to count how many mobile page views there are in my 10 terabyte Apache log. So are you currently thinking about RDDs as an array? That's an interesting question. Certainly it's a sequence. But what's the difference between a sequence and an array?
Well, array, I guess it implies that it's in a single node, like a continuous chunk of memory.
Yeah, I mean, like if it's like a C-style array, it actually does have buffer and layout semantics to it. And that's actually very much what I'm trying to get at here. So
RDDs can be across several nodes.
I mean, RDDs, yeah, they're distributed data sets. So presumably we'd like to take this sequence abstraction and implement it across the entire cluster. So what would happen in this particular example if I decided to implement this sequence of operations using the most obvious way? And so what would you say is the most obvious way to start? Yeah.
So question, are we assuming that each of the nodes is only like running a single thread?
Yeah, for the sake of this whole lecture, let's just think about single-threaded nodes. The only parallelism is across the cluster. So how would you, like if I gave you this homework assignment, you now know what the semantics of an RDD are. How would you implement like a library of rdd.map to create something new? How would you implement these various things? Like sort of rough sketch in your head. What if I told you they were arrays? It would look awfully like slide 1 of this lecture, right? I would allocate an array. I would map a function onto the array. I would allocate an array for output. And I would put the results of the function call on every element in the output array. So what happens if I do that here? Yeah.
Well, data there might be not enough space in memory for the temporary array.
This is off on disk for a reason, right? So let's just say that even if it was, like I could say that I'm going to load this block off disk. I'm going to run the map of 2 lowercase. And I'm going to store the results. So I'm going to load it off disk. I'm going to create lines. Then I'm going to run the map to create lower. Then I'm going to run the filter to create a new array of variable size now for mobile views. But now I have like 3 times as much data in memory as I had in disk. Let's just say we don't filter very much. So this is going to get intractable kind of fast. You saw this in assignment 3 when you started making copies of that graph data structure. You started running out of memory really fast. And also, if I did this is basically my first slide of this lecture implementation. Yes?
The second slide, where you take chunks at a time and work with them in Jira.
But if this was an array, I can't do that, right? Because an array I can ask for any element of an array at any time. But this is not an array. This is a collection. And the only way that you can touch the data in the collection is either through one of these operators or through one of these actions. And notice that there's no action that just says arbitrarily give me sequence element I. Okay? So that's exactly right. So the way I would like you to think about this is let's think about this sequence of operations and let's think about processing it chunk by chunk. And let's think about processing it chunk by chunk, starting with the chunks that already exist out there in disk. And so what I'm drawing here is I'm drawing the dependencies between a chunk of some RDD, or I'll call it a partition, the backing store partition of some of a downstream RDD, and the arrow points to what data is required to compute this box. And so if I want to get the first set of the mobile views, I have to get the first lowercase elements. If I want the first lowercase elements, I need to load the values from disk. If I need to load the values from disk, I have a block I need to go get. Right? So the black lines are showing dependencies between these various sections of the RDD. Good. So how would you implement this using some of the tips that the first two slides? Like, what is the right flow of things? So one answer would be I take the entire terabyte data file, I load it into disk, I now have a many terabyte allocation. If it's too big, I buy more nodes to my cluster until it fits. Then I do the 2 lower, which creates another 10 terabyte allocation, and so on and so on and so on. So if I gave you this assignment without talking about MapReduce, how would you have implemented this program if I just said this is what it has to do? Let's say I gave you a spec in English text. Yeah.
I mean, the only time when we actually needed to keep something in disk was when you said to persist that data.
Uh-huh.
So we don't need to actually keep any of the intermediate steps in disk, so we can just grab a chunk from a block,
Yeah.
through all of the intermediate steps, and then put the output like back on disk or something.
Exactly. So if I didn't set up the lecture this way, and I told you I just want you to count the number of lines in this file that are a mobile client, you would write this code. While not end of file, read line, 2 lower, if it's mobile, count plus plus, done. Working set size is 1 integer and maybe 2 lines of the file. And I would repeat this by doing it in parallel across the cluster, each of them using different parts of the file, right? This code would take 0 extra memory, be easy to parallelize, and you'd be done, right? So the RDDs, if you actually look at the implementation of RDDs, so this slide might be a little bit hard, and I apologize, is now let me start thinking about how we might actually implement an interface that gets me very close to the sort of like hard-coded thing that I did here. So imagine you had an RDD object, and we wanted to create an RDD from a text file, right? So I might say RDD create from text file, give it the file name, create an RDD object. And then if I ever wanted to count the number of elements of the RDD, I could say, well, while the RDD has more elements, get the next element and increment the counter. So I just implemented the simplest action here. So what is the implementation of next? Well, if this is an RDD from a text file, next is just readline, and has more elements is not EOF. If the RDD is anything but the source, if it came from some other RDD, next is just take the parent's next and then call the function on it, call 2 lower. And I could do the same thing for filter, like saying while the parent, the upstream block has more elements, while the parent RDD is not done, keep grabbing the next one until one of them passes my predicate and return that. So you can imagine that if I just started with this top level code and I had a collection of these RDDs, if I wanted to just implement count, I would say, okay, take the last RDD, which would be mobile views. If I wanted to count the number of elements in it, I could say while it has more elements, count plus plus. Next would call mobile views.next. Mobile views.next would come from the filter, which would call next on its upstream thing until it produced an output. And this next would end up calling from map next, which would apply 2 lower to whatever the next thing produced. And this guy would come from the text file, which would read the line from the file. So you can see how I've now created an API with just 2 iterators, next and has more elements, that actually would give me the exact same data flow as this thing that I decided to hard code. Okay. So if these are the dependencies, now you know how to schedule it. But I think it would be useful here for us to stop. And can somebody tell me how, if these are the dependencies, how would you write the scheduler for Spark? What's the order in which it will run this program? And there's 2 things to decide. What blocks, what parts of the output RDD mobile views get computed by what processor, by what node? And what is the order in which that node will execute its computations? So let's talk through both axes of how to get this right. Okay.
So block I is on some node, make that node process block I.
Yes?
And then once you're on a node, or sorry, the node granularity is at like the file level, right? And then like
Sure.
within the node, just like block by block, so that everything.
So if I want to produce a section of mobile views, I need to say, okay, this mobile views depends on the first some number of elements of, like if I want to produce the first 1,000 elements of mobile views, I would say, okay, this node is going to produce some section of mobile views. Mobile views depends on lower, which depends on lines, and look, this is all the data I have from the source of the lineage. So I could just start calling next on lower. When I call next on lower, lower will call next on lines. Lines will call read line. Return a line to lower. Lower will call to lower. And then mobile views will filter. And we can just keep doing this. And so we get exactly the same pattern as what I described, what I do by hand. So, or you can think about it in a chunked way. We'll load a chunk off disk. We'll lowercase a chunk. Then we'll filter the chunk. So you could always do it at a chunk granularity like my slide 2. So this is now the perfect data movement pattern. There's a lot of function calls in here, which should probably scare you. But compared to reading off disk, we're kind of looking OK. Notice how there's no communication at all between nodes here. Is that since this is just a bunch of maps and filters, to produce an output, we only need to get the data from this node. There's actually only one place where there needs to be global communication, which means I need to actually, to get the total count, I need to get the count from all of these across the thing, which is nothing. So this is really convenient because now no communication across my cluster, no extra disk I/O, and not a ton of memory. But let's think about a more complicated example than just like map and filter. What happens if we have reduce by key, which is a valid RDD operation, which says, hey, look, take all of the elements in this RDD, which are key value pairs, create a new RDD, which every element is a key value list pair. And to do that, I now have to sort, to do this global sort, right? So I have to wait, I have to take all of the key value pairs, and I need to send them across the cluster, like what you were suggesting, to the appropriate node. We used to do it on disk, but now we're doing it through memory. And how does that change how you can schedule this computation? So before, I could say, you know what, I'm going to read a chunk, and then I'm going to do lines, and I'm going to do lower, and then I'm going to filter the thing, and none of this has to remain resident in memory. The only thing I need is the mobile views, and then I'll just count the mobile views, and I destroy everything here. Now think about how you might implement this operator. Yeah.
I guess what we can do as a scheduler is beforehand decide which node will carry which key if we know the keys beforehand.
Yep.
And then as we see those keys, send them to those nodes.
We can send the keys to those nodes, correct?
Not wait until the whole process finished, so that the keys might have arrived to that node by the time we finish.
Absolutely, we can do that. So let's just say that we only have 4 keys. You know, we have Safari, Chrome, whatever, and whatever. And we're gonna assign the keys. We're gonna hash the keys to a node ID. So that's how we assign them to nodes. Okay. So that whenever any upstream computation produces a key value pair, it will send that key value pair to the node that owns the key. So those are the black lines here. One second, Isha. And then remember that the type. Let's go back to reduce by key. The type of reduce by key is I can't call the next downstream function until I get key paired up with the sequence of all the values that have that key. So previously, in this slide, as soon as I produced a value here, I could immediately consume the value here. And I could then immediately consume the value here, and I could delete. Everything else is gone. Can you do the same thing with this pattern? Oh, Isha, you had a question.
Yeah, so like what if like there was this one, I mean like Chrome is supposedly like popular with everybody, so
Yeah.
like the data for the Chrome key is overflowing on the node.
Yeah, I mean, MapReduce and Hadoop don't handle that case very much. They're assuming that you have a ton of keys and that they distribute well over the cluster. So that any one bucket is not considerably large compared to the whole data set as a whole. So most implementations do not do anything fancy about that. But let's just assume that's not going to occur here. Maybe there's one, maybe Opera sits over here and nobody uses it, so we're just not going to use that node. Right? Right? Bad workload balance, but we'll deal with it. But I'm actually saying, when can we start processing the downstream thing, which is I want to run, let's say, a map on the result of reduced by key? So notice that, yeah, exactly, because maybe the last item in the upstream RDD happens to be Safari page view. I cannot start running the computation on Safari, list of page views until I have that whole list. And there are no bounds, because this is completely data dependent. So unlike this example, where I had a very efficient implementation, as soon as we produced an element here, we could consume it. As soon as we produced an element here, we could consume it. On this example, we cannot begin to consume the output of reduced by key until the entire reduced by key has been completed. And what's the implication of that? There's a very bad implication of this. Oh, I need a barrier between map and reduce, so I might have some parallelism problems. But there's a much worse implication of that, even than that. So that's one implication. I might, yeah? Right, that's similar to his comment about the barrier. Like, for example, if one of these yellow nodes was a straggler, then all the, I can't get started on the next operation in the cluster until all of the reduced by keys are done. Yes?
Since your data doesn't fit in memory, you have to go to disk.
That means that I have to keep around the entire output of the RDD, probably shove it out to disk, or use a ton of memory. I can no longer stream the computation because I cannot start consuming until I've produced everything. This is not good, right? So this is why, so it's interesting that MapReduce came up with this very, very useful, powerful primitive, but the primitive happens to become like a worst case primitive from a computational efficiency. That's why it's so powerful. Everything can go to anything. And there's no way to know a priori what the limits are. Whereas if I'm using map or filter or some of these other operations, I have operations where I can exploit the producer-consumer locality.
I think we can ease this part, right? Like if you did a group by key for a node, and then say the first node is supposed to receive all the keys for all the values for Safari.
Yes.
Now, when we know that node 1 is sending Safari to the first node, and then suddenly starts sending nodes for like Opera.
Yeah.
So at that point, you know that node 1 will never send you anything more for Safari. And then when
You know that node 1 will, but you don't know the other nodes won't send you more for Safari.
Like, so once you're done seeing like Safari results from every node, you can start consuming Safari for...
Absolutely, absolutely. But what if the last line of the file is a Safari result?
No, but that's what I'm saying. First do a group by key on the local node.
You do a group by key on the local node. Okay, got it.
So,
And then you could say, that I guarantee you I will not, there's an optimization that you're proposing, which is saying, if we know that we're going to have something followed by a group by key, we could optimize that by reordering the word and then being able to send a token saying you won't get anything more. Maybe that's better off. That's true. That would actually work. It means you've reordered the computation. These are sequences. They're ordered sequences. So you're going to have a small change in semantics as well. But yeah.
Why don't
That's a good
we
optimization.
start processing the keys while we're receiving them? Why
Because-
do we have to wait for all of them?
Because the operation that you are performing, the application provided function. Remember when we wrote our reducer, it took as input the key and a list of all of the items that are associated with that key. And it was guaranteed, the contract was that you got all the items associated with the key. So the code was written assuming that that was all the items.
But you're receiving those items with the key.
Those are not the semantics of the interface. The application gets one function call saying, here are all the items. Now, if you look at a modern MapReduce implementation, they have another type of reducer, a combiner, which actually works in the streaming setting as well. So that's what you're proposing.
Yeah.
Yep. So you could say that for some applications, such as actually the one that I have on the screen right now, that type of associative reduction would have been just fine, and that's true, and that's why they had to add that feature into some of these APIs afterwards. Okay. So where was I? Here's another one that's actually kind of interesting. So imagine the join operation, which takes names and values here, the same names and different values, and produces a new RDD, which is names, comma, both values. So let's start at the bottom, actually. Imagine that my original RDD was distributed across the cluster by key. So the elements of the RDD, we hash the key, and that's the node that we stored the value on. So here we hashed kvon to node 0. And so over here in this RDDB, we also hashed kvon to node 0. And so there's a string to node ID hash. And I use the same string to node ID hash for RDDA and RDDB. And then I joined RDDA and B to create RDDC. So if A and B use the same partitioning scheme, then all of a sudden, there is no dependency on data across nodes. We can perform the join very, very efficiently. If I happen to, in the top diagram here, I used a different hashing scheme for A and B. And I created a situation where the exact same operation, join A and B, is extremely now inefficient because now I just induced all-to-all communication to join up the values. So Spark actually gives you, let me jump in right in here, is Spark actually gives you control. So an RDD is supposed to be this abstraction. But it actually how it gives you primitives to just kind of like Halide in a sense. Here's how I want you to distribute the data because it's so important to get right. So here I'm saying I made a hash partitioner which takes a string and hashes it to 100 bins. So this would be like a program written for a 100-node cluster. And then I said for these two different RDDs, which are key value pairs, I would like you to use the same hash partitioner, which means that this particular join could be implemented by the runtime very efficiently. However, if I used a different hash partitioner, the runtime to implement the join would be moving data all around the cluster. Okay. And then another scheduling primitive is I can call rdd.persist. rdd.persist says, hey, even though you could immediately consume this thing, I would like you to go ahead and store it out in memory because I'm probably going to use it again later in my computation. So it says, oh, I'll go ahead and burn the memory and store this thing, and you'll call persist on something that you think will fit in memory. So that might be something if you're doing an interactive job where you put a big data set in memory, you're going to ask a bunch of different questions about it. Okay, so let's think about the scheduler a little bit here. So imagine that we have this lineage. So I gave you a much more complex one now. So the output is RDDG. It has 3 partitions. Every partition of RDDG depends on a bunch of different partitions from RDDF and 1 partition from RDDB. And that RDDB has been, okay, so how are you going to schedule this thing? This is an interesting little problem that I would love to actually ask as an assignment next class, or next year. So, okay, so we need to produce RDDG partition 0. We certainly need to produce RDDB partition 0. And we need all of the partitions of F. So that means that we need to run all of these partitions of F. And to compute RDD partition 0 of F, now we're back in the easy case. We can compute RDD D partition 0, and then immediately, and also compute C. So what we can do is we compute a piece of C, immediately consume it in D, and then produce F. And then we'd have to go over here and produce F1, F2, and F3. And we need to keep all of these around. Why? Because they're all needed to produce 1 output partition of this. I could have decided not to keep them around, and I could have done the following. For this, okay, I'm going to compute this, boom, boom, boom. I'm going to compute this, boom, boom, boom. This one, boom, boom, boom. And then I'm going to consume it, delete all of those, and go back and do this one, and then just follow the lineage again and recompute everything I just computed. So in any situation where there's this all-to-all, it's probably going to be a better idea to try and materialize and store, even if off on disk, all of the partitions, because you don't want to recompute all of these partitions every single time that they are used. Yep.
Basically, the burden of planning is pushed to the program.
It's a little bit of both. Like you could let Spark do it, and Spark is probably going to say for any operation that's sort of an all-to-all, I'm going to materialize the thing. And for every operation that's not, I'm going to produce or consumer it.
So does it provide like a basic planner for these kind of things?
You mean to give you introspection on what happened? Or first of all, it does implement the scheduler. So I just gave you how I would do it off the top of my head. And theirs is probably way better. But it also gives you the two primitives, persist and partition, that allow you to set constraints on the schedule that is used.
So they're like directives.
They're like directives because they can be hints. Because if you say persist this in memory, in fact, they even have persist reliable, which says persist this on disk so that if I lose a node, you won't recompute it. So there's a bunch of little scheduling primitives that you can say to give it strong hints on what you think the right schedule should be. Okay, so one of the nice things about purely functional representation is, first of all, we can reorder the computation all we want. So we get producer-consumer locality. And the other thing, which was one of the more motivating reasons, was that we now know that if I lose a part of timestamps, I now know what computations I need to do to get it back. So this is by moving to a functional representation where all the dependencies are known, we now have a way of becoming resilient. So imagine, this is that same example, imagine that node 1 just crashes in the middle of a computation. What do you do as a scheduler to get back sort of the partitions that I had of the RDD that happened to be on node 1? So node 1 just crashed. You just lost all of the data in timestamps and all of the data in lines and mobile views that was managed by node 1. One exception, meaning the stuff on disk, assume it's a resilient file system, so you can get the data on disk. What do you do as a scheduler if in the middle of running this, node 1 crashes? I just lost all my yellow boxes, all my temporaries and intermediates. Really good. Can I get it back? Am I screwed? In MapReduce, I was in pretty good shape because remember, all the intermediates got written out to disk. So I could just have them loaded off disk by some other node. And I can continue on with my computation. How do I get back the partitions of timestamps and mobile views? Now, yeah, you do it like assume you have access to the disks. Because actually in HDFS, all of these block partitions would be replicated on other nodes as well for redundancy. So just imagine you can always get back to the original source of the lineage.
Well, then chop up the blocks to 3 pieces and then stream them to the rest.
Yeah, exactly. I mean, we know exactly how to recompute those values. In fact, actually, in this example here, I said that a valid scheduling strategy would be to recompute them if you wanted to throw them away. If we lose a node, we can do the exact same thing. We can say, oh, we just need to redo the lineage for that part of the output. And we'll just walk up the chain and recompute everything that's necessary. And now partitions 2 and 3 are on the other nodes. So because you know how to recompute any value that could ever be computed by the computation, you can always go back and get it. So here are some initial results from the Spark paper where they were comparing Spark here to Hadoop MapReduce, where we started the computation at. Hadoop VM is actually, they put the data in memory. The file system data was cached in the buffer cache. It was also binaryized. It was binary, not a text file in this case. So what are some things you notice about the graph? So this is two iterative algorithms, like k-means clustering, on, I can't remember what the actual input data was, but it was like 100 gigabytes of data on a 100-node cluster. And this was k-means. And so this is the amount of time for the first iteration that loaded off disk. And then all the subsequent iterations were operating on a materialized view of memory. Except on Hadoop, all iterations came off disk. So what are some of the things that you're noticing, first of all? What? Spark is really fast. Pretty fast, right? Like so first of all, why are all the subsequent iterations faster than the first one? Because the inputs are coming from memory. You do not see that speed up in Hadoop because it's coming from the file system every time. Okay, good, that's good. Yeah?
Why is Spark faster in the first iteration? Because if there's extra logic to like set everything up, shouldn't it be slower?
That's a pretty good question. I don't have the answer, and I don't think it's actually in the paper. I should ask. I don't know the answer to that question. There's no fundamental reason why it's faster. It could be better engineered or something like that. I don't actually know. This should start giving you a sense of where I want to go with this discussion. This is k-means clustering. Everybody knows what k-means clustering is, right? It's k-mean clusterings of data points in a text file. The baseline implementation on every iteration of k-means was parsing the text file. So that's a little frustrating. Hadoop VM is actually putting all of that data off disk in memory, but still accessing it through file system abstractions. And this gives you a pretty good sense of what the overhead of the software stack going through the kernel is, because this was data that was in memory too. And look at the difference in performance between those two. Yeah. On which one? Hadoop VM is saving all the intermediates in memory.
But Spark is not.
Well, in this particular case, this is k-means clustering, and so the main intermediate actually is persisted. But you're absolutely right. Okay, so a couple of takeaways here. So things are looking pretty amazing, right? We went from 139 seconds, on average 70 to 60 seconds to 3. That's like 20 times faster on a 100-node cluster. Pretty awesome. Like in the other one, it was in k-means. Because the intermediates, I think, are bigger, you see less. You see like a 3 or 4x speed up. And the redundancy. Okay, so I want to close this lecture with a little bit of a reality check. Here's the reality check. This was a paper published earlier last year. It was called Scalability at What Cost? And what they did was they said, like the scalability thing is awesome. We're scaling out to hundreds and thousands of nodes, but my stopwatch performance is not so good. So what they did is they took some of the best known implementations of graph analytics. Here's your simple PageRank. Again, I'm not arguing that PageRank is the most important thing in the world in the simple form. And they took Spark. They took GraphLab that we talked about before. All these things allow you to parallelize out into large clusters. And they said, let's go run it on 128 cores across a bunch of nodes. And let's see how long it takes to run on the Twitter graph or this other graph that I can't remember. But the size of those graphs are pretty big. You see it over there on the right. Let's just make one core what an undergraduate would write, stick it against an SSD, and measure the performance. What do you guys notice? This is a 2015 paper by Google, so this is not. What is interesting to you? And by the way, if you do very simple things like your assignment 3, that 300 seconds just went to 110, one core, one thread. What is striking to you? Sorry? What? What is striking to you?
Drop the course and just focus on single things.
But these systems scale. You could use hundreds of nodes.
I also read an article about.
We're almost, 1 second. Okay, go ahead. Yeah.
It was about that.
Okay.
Some engineer, instead of using Hadoop, he did like Unix pipes and stuff, like piping stuff together.
Exactly.
And it was much faster than it. But that's only because the size of the input was not big enough to warrant the overhead of using these sophisticated algorithms.
Correct. How big do you need to get? I mean, that's a big graph.
That's small.
Okay. So we can keep moving. We can go to label propagation, where the Spark implementation versus one thread in C. We can go to another group at Berkeley that recently did this. They did a GPU single node. So this is 50 boxes or 64 boxes versus one box. So the conclusion for this paper is a very useful conclusion for everybody to have in mind, especially in their projects. The published work on big data systems has prioritized scaling out to as many nodes as possible. And it's unclear to what degree are these systems truly improving performance, or are they just paralyzing the overheads that they themselves created? So they made this metric in this paper called cost, which is how big of a supercomputer do you need before you outperform a single thread? And they said that surprisingly, many published systems have unbounded cost. If you take the biggest graphs in the world that are publicly available, you never break even, right? And your implementation of assignment 3 is probably, for a graph that you can fit in memory, significantly better than what you do in GraphLab on a large cluster. It'd be an interesting thing to measure for those of you that are doing those kind of projects. So that's not to criticize this community. They were motivated by very different concerns of scaling out to large numbers of machines. And you can see now that disk is not the fundamental concern. We have SSDs, we have 3D XPoint, we have a lot of fast, large-scale storage technologies. This community is now beginning to look at how in the world can we more efficiently use the processors that we have, get the huge scaling, but also use a single node really well. And they're beginning to use a lot of the techniques that we describe in this class. There's an effort called Project Tungsten, which is to actually JIT compile the kernels that you hand, the lambdas that you hand to Spark, so they can do things like exactly what ISPC generates the vector kernels, or target CUDA or GPUs and things like that. Because this is just not tenable to be able to say, look, if we're going to scale out, we're going to give up 1,000x. Right? The benefits of reliability are certainly meaningful at 1,000 cores, but nobody really worries about reliability when you can do the same thing on one machine. Okay. And then conversely, the distributed systems community has done a lot of really amazing work on how to handle large numbers of machines like utility, like a utility. Computing is a utility. They have really worked out elasticity and things like that. So imagine that you're running these scientific computing jobs, and halfway through it, you're like, I would love to be able to scale up to 100 nodes because I need to get this job done or something like that today. The scientific computing frameworks are not very good at any of that stuff. So they have a lot to learn from the distributed systems community. So in the next couple of years, you're probably going to see a fusion of taking elasticity and some of the ideas from assignment 4 and getting them more first class into supercomputing workloads. You're going to see the distributed systems community going, this is just insane. We need to make use of our modern normal hardware much, much better, and adopting some of the high performance techniques from imaging, graphics, and those kinds of things. So the summary of Spark, in some ways, is that if you're doing things like graph analytics, various types of machine learning, that storing your intermediates in the file system is not a good idea. And so in hindsight, that sounds kind of silly. But this was actually a very interesting problem that a lot of people were concerned about at the time, and they kind of just took principles from out-of-order execution or DAG scheduling and were able to apply it to solve the problem here. So if you're interested in this stuff, there's a lot of frameworks built on Spark. GraphX is sort of something like, it's similar to GraphLab built on Spark's abstractions. MLlib is a set of machine learning a toolkit built upon Spark. Spark SQL is you can actually make a database query and get the results of the query back as an RDD. And the last thing I wanted to say is that if you're interested in this kind of stuff, and you look at what the supercomputing is doing, I think there's a system called Legion, which is a fairly interesting system that's tried to address similar problems, but come at it very much from a scientific computing perspective. And so some of the things that Spark really does well, Legion does not do well. Legion has a much richer notion of, instead of a collection or a sequence, they actually give you resilient distributed data structures, like entire trees and things like that, much richer set of data structures. So if you're interested, that's a useful thing to go take a look at. Okay, so that's the lecture today. And I would like to make sure that you don't make mistakes in evaluating your projects when you show me it scales on 20 nodes, and all of a sudden I ask an undergraduate that hasn't taken this class to compete with you on one thread, you better win.